Section 6.4 would be long even if there wasn't theory. There's theory. I feel like this might be a 4-part video. We're introducing a new topic that we used to cover in intermediate algebra that we don't anymore. And that topic is logarithms. Logarithms are a type of function that are used to answer when type questions. For example, if I wanted to know when the population of the United States will reach 10 billion, logarithms would be used for that. Or when the amount of a certain radioactive element, when 20% of a certain radioactive element will be left, logarithms would be used to answer that sort of question. They're great for answering when type questions. That doesn't tell you anything about the structure of logarithms and what they are, so let's try to get this down here. So this logarithm right here, this is a logarithmic function. I read this as the log base 10 of 100. The 10 is called the base of the logarithm. The 100 is called the argument of the logarithm. Again, that doesn't really tell me anything either. This logarithm is asking a question, and all logarithms ask the question, the base to what power equals the argument. That's what every logarithm is asking. So the statement, the log base 10 of 100, to answer it, the question it is asking is 10 to what power, the base 10 to what power equals the argument. If you know the answer to that question, then you know what this logarithm is equal to. If you don't know the answer to that question, then you're going to be bound to your calculator or a chart that I've created. So if you know your powers really well, this section is not so bad to kind of stumble through. If you're horrible, if I asked you what 2 to the 5th power was and you didn't know that it was 32, then you're going to be bound to your calculator a little bit in this chapter, or a chart that I created here that I'll show in a little bit. But the log base 10 of 100 is equal to 2 because it's asking the question 10 to what power is equal to 100 and 10 squared is equal to 100. If I wrote this statement and I asked you what is this log equal to, what is the log base 2 of 8 equal to? Well, this is asking the question, the base 2 to what power equals the argument 8. And if you knew your powers of 2, you'd know that this answer is 3 because 2 cubed is equal to 8. On my super cheap calculator, it has a log base button. If I wanted to do the log base 2 of 8 on this calculator, it's so beautiful, I just type it, and I can tell you that it's 3 mindlessly. Any other calculator I have either doesn't have the log base, that's what this calculator doesn't have, that subscript potential, or the log base is hidden somewhere. I think on this calculator, maybe it's under math. I forget where it's at. I should have, yeah, there it is. Under math, if I go down to log base, then I can do log base 2 of 8. So real quickly, if I do math and arrow, 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 arrow down forever, or arrow up, I get to that log base. This calculator, I hit math and arrow down no matter where I go, it doesn't have it. This calculator is too old to be able to do that. There's a way to do it on this calculator using a rule of logarithms that we're going to learn in a bit. I don't want you to be bound to your calculators. I want you to understand logarithms well enough so you don't need to use your calculator. And that's what we need to get into a little bit now. So before I jump into some lectures, I made a bunch of tables that will be available if you open up this section. And for a bunch of really common values, I wrote what the logarithm is equal to and why it was equal to that, or why it wasn't equal to something. So this first chart, I have logarithms base 2, starting with a negative number, working all the way up to 256. The first one asks me to find the log base 2 of negative 1. And the log base 2 of negative 1, when I see that logarithmic expression. This is asking the question 2 to what power is -1? And we graphed exponential functions in the last section, and we found that when we raised 2 to a negative power, we got a fraction. If we raised 2 to a positive power, we got a big number. There's no solution to this. There's actually a solution that has eyes, but we're not going to do any logarithm with eyes. I did it at one point in my life, but I don't even remember how to do them. I remember them being complicated. So this doesn't have an answer. We could say there's no answer, no solution. Technically, it has an I in it, so I wrote it's a non-real number, because 2 to any power is not going to be a negative number. It's always going to be a positive number. If I raise 2 to the -2 power, it's not going to be a negative number. 2 to the -2 power is 1/4. If I raise 2 to like the 3rd power, it's 8. There's no way to raise 2 to a power and get a negative number unless that power had an I in it. So that one has no solution. The next business here says, what is the log base 2 of 0 equal to? And for a similar reason, there's no solution to this. This is asking the question 2 to what power is 0? And 2 to any power is either a fraction with 1 in the numerator or some bigger number. I can get more complicated and talk about decimal exponents, but I'm still not going to be able to get 0. And this isn't even an I. But logarithms for base 2 of negative numbers and zeros, there's no answer. There's no logarithm base 2 of -1. If I try to do this on this calculator, it's going to give me some sort of error. If I try to do the log base 2 of -1, gives me a math error. Similarly, if I did the log base 2 of 0, also gives me a math error. Logarithms only work for positive arguments. Next one asks me to do the log base 2 of 1. And log base 2 of 1 is asking the question 2 to what power is equal to 1? And because 2 to the 0 power is equal to 1, the log base 2 of 1 is equal to 0, specifically because this is saying 2 to what power equals to 1, and because 2 to the 0 power is equal to 1, the log base 2 of 1 is 0. Next one down, log base 2 of 2. This log base 2 of 2 is asking the question, the base 2 to what power equals the argument. The answer is 1 because the base 2 to the first power equals the argument. I'm not going to go through all of these, but I'll go through a few more. The next one on my list says the log base 2 of 4. What does that equal to? If I didn't have this table in front of me, this is asking the question, the base 2 to what power is equal to 4? And the answer to this logarithm base 2 of 4 is 2, specifically because the base 2 to the second power equals 4. The base is kind of irrelevant. I can move down to a different base. Here I have a base 3, and let me look at the log base 3 of 0 real quickly. The log base 3 of 0, I have no paper, I'm going to get some paper. The log base 3 of 0 is asking the question, three to what power is equal to 0? And just like with the base of 2, 3 to a negative power is going to be a fraction. It's not going to be equal to 0. 3 to a positive power is going to be an integer. And 3 like to a decimal power is like a square root. 3 to the 0.5 power is a decimal, but they're all positive. There's no solution to this. Logarithm base 3 of 0, there's no number that satisfies that because there's no power that I could raise the base to get the argument. Let me just bump down to a more complicated one, like the log base 3 of 81, which I wrote equals to 4. If I asked for the log base 3 of 81, this is asking the question 3 to what power equals 81? And if you know your powers of 3, then you could just say, well, the answer is 4 because 3 to the 4th power is 81. Not everybody, not most students know their powers well enough to rip logarithms off in their head. So that's why I made this chart up, so you don't have to rely on your calculator to go, oh, what is the log base 3 of 81? Oh, well, the log base 3 of 81 is 4. So this chart is designed to help you get some common logarithms, and it tells you why the logarithm works. If I was asked to find the log base 4 of 16, if I was asked to find the log base 4 of 16 and I didn't know that it was equal to 2, I might be able to reason it out, because this logarithm is asking the question, the base 4 to what power is 16, and if I knew that 4 to the 2nd power was equal to 16, then I'd know the logarithm base 4 of 16 is 2. And again, on this lovely calculator, it's the only calculator that I would probably do logarithms on like this because it's so fast to do. There are a couple things that we should talk about in terms of bases that are common bases that are tricks. And that's these two levels of my chart. These two levels of my chart, I don't see bases. This level I see log of -1, log of 0, and I don't see a base. If no base is written, these are all assumed to be base 10. The logarithm with no base written is assumed to be base 10. So this right here, this line, I could have written it as the log base 10 of 100 equals to 2. And the reason this works, so when I wrote the log of 100 equals to 2, or when I typed the log of 100 equals to 2, the question that the log of 100 is asking is 10 to what power equals 100? Because the log of 100 is the same as the log base 10 of 100, and this is asking the question 10 to what power is equal to 100? And because 10 to the 2nd power is equal to 100, the log of 100 is equal to 2. It would be nice if you can do the logarithms without your calculator or without looking at the sheets that I typed up that you can find in the problems for this section. But if you can't, you can't. I can live with you having to do these by hand or with technology or with a table. Definitely there's some teachers that wouldn't let you use your calculator or a table to get these logarithms, and they'd make you just learn how to do them. So one logarithm that comes up a lot, so much that it doesn't have the base written, is base 10. In fact, even my inexpensive, well, it's not inexpensive, even my old calculator, the log button on it's working in base 10. If I type the log 100 on this calculator, that is the log base 10, and it's going to tell me that it's a 2. So that's a base that's so common that my calculator has a button for it. The next base that's so common that my calculator has a button for it is base E, and base E is ln. So this problem here that says the ln of 1, and I had an m written for some reason, is really log base E of 1. So this ln of 1 equals 0. That's the same as saying the log base E of 1 equals 0. That's ln is shorthand for ln. And if on this calculator I typed the ln button and typed 1, it would tell me that the ln of 1 is 0. If I use this calculator, it also has the ln feature, but I could also do ln, I could do log base E of 1. ln of 1 and log base E of 1 exactly equal to each other. They're just same. This is a shorthand for that. It comes up so often in mathematics classes, chemistry classes, physics classes, that there's a separate button for log base E. There are a couple things that we should know about logarithms, and I'm already 15 minutes into this video. That's not good. And these are the common things that if I went through with more time and went through this, the rules would be more obvious than just stating them. But the logarithm of any real number, if you look at the top row in my chart, it's a logarithm of a -1. It turns out that the logarithm of any negative number is an I, and it's not a real number. Similarly, if you look at the second row in all my charts, I'm doing the logarithm of 0 in various bases, and those are all does not exist, does not exist, does not exist. The logarithm of 0 doesn't exist. So logarithms are not defined in our class for 0 or any negative numbers. And then if you looked at the third row in each of my tables, I have the logarithm of base 6 of 1 is 0, the logarithm base 10 of 1 is 0, the logarithm base e of 1 is 0. In general, the logarithm, any base of 1 is going to be equal to 0 because this is asking the question, the base to what power is equal to 1? And because any base to the 0 power is equal to 1, the log base b of 1 is 0 in any base. And the last thing that we should notice is that regardless of the base, here the log base 6 of 6 is 1, the log base 10 of 10 is 1, the log base e of e is 1, I should know that regardless of the base, that the logarithm, if the base and the argument match up, that this is equal to 1. Because the question that this logarithm is asking is the base, which is b, to what power equals the argument, which is b. And that answer is always 1 because b to the first power, whatever the base is equal to b. This is why on that row, when I had log base 6 of 6, it was equal to 1. On this row, log base 3 of 3 is equal to 1. On this row, log base 4 of 4 is equal to 1. That's really as much as I have time for. I'd like to spend more time developing some logarithm ideas, but I need to jump into the section or it's going to be like a 3-hour lecture, and you don't want that. So the next thing we're going to do is really formalize the relationship between logarithmic functions and exponential functions. And this is kind of formalized what I've been saying. So this says if the logarithm base b of the argument x is equal to y, then b to the y is equal to x. This is exactly a more formal way of saying what I've been saying. For instance, since the logarithm base 2 of 16 equals to 4, if I did this on this calculator, log base 2 of 16 equals to 4. Remember, the log base 2 of 16 is asking the question, 2 to what power is equal to 16? So that question that's being asked, the log base 2 of 16 equals to what? The what it equals to is the answer to the question, the base 2 to what power is equal to 16? And because 2 to the 4th power is equal to 16, the answer to the logarithm base 2 of 16 is 4. This is a true equation with logarithms. This equation, if you simplify the left-hand side, it says 4 equals 4. Beneath it, I took the numbers and wrote the question that was being asked by the logarithm. So this logarithm says the log base 2 of 16 equals to 4. This is true because 2 to the 4 is equal to 16. This is an important skill, to take an equation that's written in logarithmic form and write an equivalent true statement written in exponential form. So this right here is a logarithmic statement, and it's a true statement. It says 4 equals to 4. And this is an exponential equation or an exponential statement that is also true with the same values 2, 4, and 16. So anytime I'm given a logarithm, like if I gave you the log base 5 of 125 equals to, well, what does it equal to? If I know the question that's being asked, this is asking 5 to what power is 125. If I know the question that's being asked and I know the answer to that question, then I don't need my table, nor do I need a calculator to figure out that the log base 5 of 125 is 3 because 5 cubed is 125. If I knew this is asking 5 to what power is 125, and even better yet, if I knew 5 cubed is 125, I'd know that this logarithm is equal to that. When we get into the section, I'm going to ask you to write an equation that has a logarithm using exponents or in exponential form. So I'm going to create the true statement that has an exponent without a logarithm. And the true statement is the question that this is answering. This log base 5 of 125 equals 3 because 5 to the third power equals 125. So if I'm given a logarithm, like the log base 7 of 49 equals 2, and I want to create the exponential equation that derives from this, what I would do is I'd cross out the logarithm, I'd leave the 7 as a base, and I'll switch the 49 and the 2. The statement 7 squared equals 49 is the exponential equation that I can derive from the logarithmic equation. That basically says if I have a logarithm, I could turn it into an exponential equation, and this is what it tells me to do. Scratch out the logarithm, leave the b subscripted, and switch the argument with the number or variable to the right of the equal sign. This is going to be a skill that we're going to use a lot in this chapter. And the alternative we're going to do too. This is a true statement that 3 squared equals to 9. What's the logarithmic equation that's equivalently true? Well, how do I do that? I'm going to introduce the word log. The 3, because it's the base of the exponential function, I'm going to leave it as the base of my logarithm. And I'm going to switch the roles. The 9 is going to become the argument. The 2 is going to go to the right of the equal sign. I claim that both of these are true statements. That one's obviously true. And this one, the log base 3 of 9 is equal to 2. Or the log base 3 of 9 is equal to 2. And so that's a skill I need to have. And the first 20 problems in this section, which we'll probably all will get to in this video, exactly want me to do this. They give me problems that are either written with exponents and they want me to write them with logs, or they give me problems with logs and want me to write them with exponents. They're true statements to start. They're going to be true statements in their alternate form. Problems 1 through 11 want me to create a logarithm that has a true meaning with the numbers or the equation that's given. How do I do that? I write the word log. The base for the exponent is going to be the low part or the base of the logarithm. And then I switch the exponent and the number to the right of the equal sign. So this I claim is a true statement. The top one hopefully is obviously true. And this statement, I can show you that it's true by pressing buttons if I have a calculator that makes logarithms easy to do. The logarithmic form of 2 to the 5th equals to 32, I do the same thing. I write the word log. The 2 is going to be subscripted because it's the base of the exponent. And now I need to create an argument and something to the right of the equal sign. And I switch the roles. The 32 is going to become the argument. The 5 is going to go to the right of the equal sign. I have it on my chart. I could logic it out in my head, or I could do it on my calculator to show that that's right. On this, the log base 2 of 32 is equal to 5. Or on there, the log base 2 of 32 is equal to 5. This, I don't know if it showed up in my table, but let's do this here. This is going to be the log base 4, and then switch the 1/16 and -2. The log base 4 of 1/16 is -2. That's not so common. To know that this is true because 4 to the -2 power is 1/16. Let me show you this on my calculator just to show you. It's not in my tables. The log base 4 of 1/16 is equal to -2. I don't need to know how to do this in my head, but I need to be able to take any equation that's written as an exponential equation and convert it to a logarithmic equation. And to do that, you write the word log. The subscripted, or the base part of the exponent, becomes the base of the logarithm. And then you switch. The exponent goes to the right of the equal sign, and the number to the right of the equal sign becomes the argument. There's some tricks here because E is an odd base to write. If I was asked to do the same for problem 8 to create a logarithmic equation, I can write the word log. I'm going to subscript the E, and I'm going to switch the 1 and the 0. So the E becomes subscripted. I switch the 1 and the 0. This is a true statement. This is rewriting the problem in logarithmic form, but log base E is almost never written. Usually, instead of writing log base E, we write ln. Log base E and ln are have the same meaning. If you take brief calculus, you did a bunch with ln's. Problem 10 says e squared equals to 7.39. The logarithmic version of this would be the log base e. So the base becomes the base of the exponent, the base of the logarithm. The 7.39 is going to become the argument, and the 2 is going to go to the right of the equal sign. This problem really should have a little squiggly because it doesn't exactly equal that. That's a rounded version. I'm probably consistently inconsistent. It's not ever wrong to put the argument in a parentheses, but if it's just the logarithm of a single number, I probably don't usually put it in a parentheses. The next skill I need to have are in problems 12 through 26. They give me a true statement. Like if I looked at problem 12, the log base 2 of 8 equals to 3. That's a true statement. You could see it on this chart here too. The log base 2 of 8 is equal to 3. I want to create an exponential equation. I'll write the equation without the logarithm. Super easy. This is just the reverse of what we're doing. To do this, I'm going to scratch out the log. And I'm going to switch. You can almost see an exponential equation starting to form. I'm going to switch the argument and the number to the right of the equal sign and create an exponential equation. So the 2 started off low, it's going to stay low. The 3 and the 8 are going to switch. The 3 is going to become the exponent. The 8 is going to go to the right of the equal sign. That's also a true statement. That's the exponential equation of that logarithmic form. Problem 14, if I want to write this without a log, I scratch out the log, I leave the 2 low, I switch the 16 and the 4 and get 2 to the 4th equals 16. Problem 16, if I'm doing the same instructions, write it in exponential form. I scratch out the log, the 5 remains low, I switch the 1 and the 0 becomes the exponent, and the 1 goes to the right of the equal sign. I'm creating all true statements as I do this. In problem 18, I cross out the log, I leave the 3 subscripted, and I switch the x and the 2 and get 3 squared equals to 9. I haven't been reduced, 3 squared equals to x. I haven't been reducing any of these. If I had reduced this, I would have written 1 equal to 1. If I reduce this, I'd write 9 equal to x. It's okay to do the reduction, but it's kind of hiding what we're doing right here. We're just getting in the practice for these first kind of 30 problems, going from a logarithmic equation to an exponential equation, and then backwards from an exponential equation to a logarithmic equation. In the next few problems, I'm not seeing the base, so there's a base that's assumed. In problem 20, since it's the word log is written and there's no base, the base is assumed to be 10. The logarithmic form of this is log base 10 of x equal to 4. To write it as an exponent, I cross out the log, the 10 stays low, I switch the 4 and the x, and I get 10 to the 4th equals to x. It wouldn't be wrong to write 10,000 equals to x because that's what 10 to the 4th is. On problems 21, 22, 23, it's ln. ln is shorthand for log base e. So 22 is really saying log base e of x is equal to 0. To write that in exponential form, I scratch out the log. The e is going to become the base for the exponent. I'm going to switch the 0 and make it the exponent and write the x to the right side of the equal sign. And that would be okay to say 1 equals to x because e to the 0 is equal to 1. 2 more problems and then we'll move into a part 2. I hope there's only 3 parts, but boy, there might be 4 parts to this video. 24 is asking the question, the log base e of e equals to 1, because ln is shorthand for log base e. To write this without the logarithm, I cross out the logarithm. The base of the logarithm is the base of the exponent. The number to the right of the equal sign becomes the exponent. The argument goes to the right of the equal sign. This just says e equals to e. And lastly, problem 26, because it's specifically asking me to write it in exponential form, I have to know the base. ln is convenient for calculator purposes, not so convenient for always for algebra purposes. ln can always be changed to log base e. Log base e can always be changed to ln. So here, to write this in its exponential form, cross out the log. The e is going to be the base. And then I'm going to flip-flop. The 3 that was to the right of the equal sign becomes the exponent. The argument of e cubed goes to the right of the equal sign. And that's most clearly a true statement. So that's everything for the first part of this video. I still have a big chunk of stuff left. So I think this might be the doomed 4-parter. Let me just pause right now. We'll move on to a part 2.